Hi, my name is Audra McMillan. Today I'm going to be presenting the paper Hiding Among the Clones, a simple and nearly optimal analysis of privacy amplification by shuffling. This is joint work with my colleagues Vitaly Feldman and Kunal Talwar at Apple. Let me start with a brief introduction to differential privacy, a notion of privacy for data analysis. So our goal in privacy-preserving statistical analysis is twofold. Firstly, we want to compute some statistic or do statistical analysis on our database. We also want to protect the privacy of our data subjects. Differential privacy gives a specific definition of what it means to protect the privacy of data subjects. So imagine we have two databases, P and P prime, that differ just in my data. So in P, my data is yellow, and in P prime, it is pink. And everyone else in the database is the same. Intuitively, we say the mechanism A is differentially private if it's impossible to confidently guess from the output of A whether the input was P or P prime, or equivalently, whether my data was yellow or pink. Technically, we say an algorithm is epsilon differentially private if for every possible output, the probability of seeing that output under P is about the same as the probability of seeing that output under P prime, where about the same is controlled by the privacy parameter epsilon. The model of differential privacy I just described is actually what we call the central model of differential privacy. We have a trusted central server who can aggregate the data of all of our data subjects, and we care about the privacy of the output of the central server. There's also another model of differential privacy, referred to as the local model of privacy. In the local model, there's no trusted central server, and data subjects need to privatize their data points before they send them to the central server, or send them to the analyst directly. We call the algorithms data subjects used to communicate their data to the central server differentially private local randomizers. And we can also consider an interactive version of the local model. And this is important for running algorithms like stochastic gradient descent. The local model of privacy is typically preferred in practice due to the lower trust assumptions required. However, the utility cost of using local differential privacy is high. For example, suppose that each data subject has a value between 0 and 1, and we're trying to compute the mean. The error under central differential privacy is about 1 over epsilon n versus 1 over epsilon squared n in the local model. This is a substantial difference for large n, and in particular for moderate values of epsilon, this is less than the statistical error in the central model and not in the local model. So this leads to the question, can we get the accuracy benefits of the central model without the strong trust assumptions required? One possible solution you might think of is multi-party computation. And while this can be a feasible solution in some scenarios, it's often inefficient and requires tailored implementations for every statistic. So this led people to consider a more practical solution of simply permuting or anonymizing the data points. Now we know that anonymizing or permutation on its own doesn't give you differential privacy, but in collaboration with other privacy preserving techniques, can it give you more privacy? So the shuffle model was introduced in 2 concurrent papers in 2019 by Chu et al. And Erlingson et al. So in the shuffle model, we introduced an additional server between the data subjects and the central server called the shuffler. And the shuffler simply permutes the reports sent to it by the data subject and sends the permuted reports to the central server. And in the shuffle model, we care about the output, the privacy of the output of the shuffler. And just as in the local model, we could imagine an interactive version of the shuffle model. And the critical feature is the central server never knows which data subject they're interacting with. And this again allows us to implement algorithms like stochastic gradient descent in the shuffle model. The question of privacy amplification by shuffling, which is the main topic of this paper, is the following. So suppose I have n data subjects, and each of my data subjects uses an epsilon 0 local randomizer to send their data to the shuffler. The more privacy guarantee do we get in the output of the shuffler? A fundamental property of differential privacy says the output of the shuffler is at least epsilon 0 differentially private, but is it more private? So does anonymization amplify privacy? The 2 concurrent works that introduced the shuffle model both showed that, yes, the output of the shuffler is substantially more private than the unshuffled data. So when epsilon naught is small, both of these bounds are about epsilon naught over square root n, which is obviously a substantial improvement when n is large. Erlingson et al. Showed this results regardless of the local DP mechanism used and for interactive algorithms between the central server and the data subjects. Chu et al. Showed a tighter bound in the case where the data subjects use a specific local DP mechanism called binary randomized response. Now, notice that the exponent in these bounds are different. So in the high epsilon naught regime, where epsilon naught is large, there's an exponential gap between them. We typically think of the privacy parameter as small, say less than 1. But these results actually justify the use of large local epsilon, so large epsilon naughts. If you primarily care about the guarantee of the output of the shuffler, then you can achieve small privacy guarantees in the output of the shuffler, or good privacy guarantees, with the use of large epsilon naughts. So because there's an exponential gap here, and this exponential gap matters in the large epsilon naught regime, we really want to bring this exponent down. So there were a number of works that brought this exponent down in various settings. In the paper of interest to us today, we showed that in the general setting of adaptive shuffling, so interaction between our data subjects and our central server, and regardless of the local randomizer our data subjects use, we can bring this exponent all the way down to 0.5. And we actually know this result is tight because we know the result for binary randomized response is tight, which also has a 0.5 here. For those familiar with differential privacy, we additionally show that we can obtain the same bound when the users use an approximately differentially private local randomizer. We also show that a specific mechanism, k-randomized response, amplifies better than the general case. So if all of our data subjects are using this algorithm k-randomized response, then we get the previous privacy guarantee divided by square root k. And this corroborates some empirical results by Vitaly, Gascon, and Nissim. Again, for those familiar with differential privacy, this small lie here, the guarantee on the output of the shuffler is actually an approximate DP guarantee, where delta appears where you might expect as a square root log 1 over delta in the epsilon term. And I just want to highlight some other works. I also want to give a little bit more intuition in terms of some numerical results. So on the x-axis, we have our number of users, or number of data subjects. And on the y-axis, we have the privacy guarantee of the output of the shuffler. And note that both of these are on a log scale. The red line is the exact computation for binary randomized response. So it serves as a lower bound for our general amplification result. And the blue line is the best bound from prior work. The important line here is the orange line, which is our amplification band computed numerically. And we can see that once n is bigger than 10 to the 5, we're getting privacy guarantees in the output of the shuffler that are less than 1, despite the fact that the local privacy guarantee is 6. And once we're up to about 10 to the 6, we're less than 0.1. So we're getting really quite strong privacy guarantees in the output of the shuffler. Okay, so now I want to turn to an intuitive outline of the proof of our amplification result. I want to point out that this proof actually gives us a way of numerically computing our privacy amplification result that'll result in much tighter privacy guarantees than our closed form solution. To aid clarity, we're going to focus on a simplified setting for the remainder of this talk. So suppose we have n data subjects. Our data subjects all use the same epsilon 0 local randomizer to set their data to the shuffler, and they're all going to send them at once, so there's no interaction here. Okay, now let P and P prime be the two neighboring data sets from our definition of differential privacy. So they differ in the data of a single individual, the green person and the orange person. And for clarity, let us imagine that the other n minus people are identical. Remove this assumption again, doesn't introduce complexity into our proof, but does introduce some notation that we don't want to deal with. And our job is going to be analyzing how close the distribution of the output of the shuffler is on P and P prime. So I first want to outline the main key ingredient of our intuitive proof. So suppose that A is an epsilon 0 local randomizer. Then for our two data subjects, our green person and our running person, this gives us the following property on the probability density functions of A of the green person and A of the running person. So imagine these graphs represent the probability density function of the mechanism A run on the green person and the running person. By assumption, E to the negative epsilon naught times A of the green person lies entirely below A of the running person. So we can write the running person's PDF in the following way. And now, normalizing this remaining mass of this other stuff, we can interpret this as saying that the running person's distribution can be obtained by sampling from the green person's distribution with some probability and sampling from some other distribution with the remaining probability. And we can decompose the running person's distribution in the same way with respect to the orange person. Averaging the two equations, we have that we can sample from A evaluated the running person by sampling from A evaluated the green person with some probability, A evaluated the orange person with some probability, and some other distribution with the remaining probability. And it doesn't really matter what this other distribution is. What's important is that we can compute it given knowledge of P, P prime, and A. Okay, so now we've established the following decomposition of the running person's distribution. Now we're going to imagine running a shuffle mechanism on the databases P and P prime. And remember, what we care about is how close the distribution of outputs is on these two inputs. So first, imagine the green and orange people simply saying whether they are green or orange. Then each running person is going to randomly choose which mixture component they're going to sample from. Then they're going to sample from the corresponding mixture component. So this results in each data subject reporting a sample from the mechanism A evaluated on their data point. And the shuffler then shuffles all the local reports, resulting in this final output. Now, notice that when each person samples from their mixture component, the only thing that matters is whether the mixture component is green, orange, or running. Where the mixture label came from doesn't matter at all. So we can swap the order of the shuffling and the sampling without changing the output distribution. And now the sampling is simply post-processing. Doesn't matter whether the input was P or P prime. We do the same post-processing step. Now, key feature of differential privacy is that privacy guarantees are preserved under post-processing. So the closeness of the two distributions on outputs we have here, these are only closer than the two distributions given before the post-processing step. So for the purpose of the privacy analysis, we can ignore the post-processing step and just look at the distribution on outputs of these two mechanisms. So now, after shuffling, the only information that remains is the number of green people, the number of orange people, and the number of running people. The distribution of these follows a simple multinomial distribution, but just for intuition, let's pull out the distribution on the green people. This is simply a pair of shifted binomials. It's really easy to show that these two distributions are close in terms of the measure relevant for differential privacy. We can also numerically compute how close they are. So actually doing this analysis of how close these multinomial distributions are gives us our amplification result. So the crucial insight in our intuitive proof was to narrow down to these two neighboring databases, P and P prime, and write out post-processing in terms of just these two databases. This allowed us to reduce to that simple mechanism. So our general proof follows the same structure. So this diagram outlines the general proof for adaptive shuffling using any pure DP local randomizers. So again, we have a simple protocol on the two databases P and P prime, and we can view all of the complexity of the adaptive mechanism as post-processing. A key difference here between this and our intuitive example is that we can obtain a tighter guarantee by additionally using the fact that the distribution of outputs on the green and the orange people are also close, a fact that we didn't use in our intuitive proof. For those familiar with differential privacy, notice this allows us to report the value of the first data subject, the one that's different between P and P prime, using binary randomized response. So again, because privacy guarantees are preserved under post-processing, we only need to be concerned with the divergence between these two very concrete, quite simple multinomial distributions resulting from the output of this simple mechanism. So we can analyze the closeness of these two multinomial distributions in a number of ways. We can get closed form solutions, analyzing them theoretically. We can analyze the closest numerically. We can also analyze it in numerous different measures in order to get different notions of privacy. So if we analyze something called the epsilon delta indistinguishability, this gives us the differentially private amplification results that I advertised kind of at the beginning. So if we give a closed form theoretical analysis, we get this formula here, which will be stated earlier, where our exponent here is the 0.5 that was promised. We can also analyze this numerically to get tighter bounds. So here I have a graph similar to the one I gave earlier on, but on the x-axis, I have the local epsilon, epsilon naught, and on the y-axis, I have the privacy guarantee of the output of the shuffler. And again, the red line is a numerical evaluation of binary randomized response, and it serves as a lower bound to the general amplification result. The purple and blue lines are the best results from prior work. The orange line is our bound computed numerically. And the green line is that given by our closed form solution. So notice that the orange line is very close to the red line, our lower bound, when epsilon naught is small. There is a bit of a gap when epsilon naught is larger. I'm actually not sure whether this is inherent or not. So we can also analyze the difference between these distributions in other measures. So if we analyze it in the Renyi divergence, we get a result of something called Renyi differential privacy. A theoretical bound for privacy amplification in terms of Renyi differential privacy was given in follow-up work in Gerges et al. In 2021. So hopefully by now you have some intuition of the proof, as well as some understanding of how we can analytically evaluate the privacy guarantees of the output of the shuffler using our proof. So I want to end with an example of how we can use this result to obtain algorithms that are simultaneously almost optimal in both the local and central models of privacy. And the example we'll focus on is frequency estimation. We have a finite universe of k elements and a data set of size n on this universe. And our goal is to estimate the vector of empirical frequencies differentially, or just the histogram over this data set. This problem is well understood in both the central and local models of privacy. And our goal is to design an algorithm in the shuffle model that has the following properties. So it has low communication, it's single round, so a single message per user. It has some local DP protections, and the error matches the optimal error in the central model up to a logarithmic factor. A shuffle DP protocol that satisfies this final requirement for this problem was given by Ghazi et al. In 2019, but it doesn't satisfy any of the other conditions. And what we'll show is that we can actually generate this algorithm quite quickly using our amplification result. The privacy amplification by shuffling result holds for any local randomizer. We can borrow directly from the local differential privacy literature to give us algorithms in the shuffle model. So for frequency estimation, we're going to borrow from Talwar et al. And Chen et al., who both designed single round algorithms in the local model that have optimal utility and low communication. So since we want the output of our shuffler to be epsilon differentially private, we can tailor the privacy guarantee of our local protocol. So this value epsilon naught, given in this formula here, so that after shuffling, our privacy guarantee on the output of the shuffler is epsilon differential privacy. Since each subject is simply using a local randomizer from Talwar et al. Or Chen et al., its algorithm, it's still going to be low communication. What our data subjects are doing doesn't really change. And it's still going to be single round. We also have some local differential privacy guarantee, of course, in the form of this epsilon naught here. And as discussed, the shuffled output is epsilon dp as required. The final utility guarantee is also immediate from the local DP results by simply plugging in our formula for epsilon naught into the utility guarantee of the local DP algorithm. And this utility guarantee is optimal up to logarithmic factors. So we've almost immediately obtained our desired algorithm by just borrowing from the local DP literature and using our privacy amplification by shuffling result. Finally, I want to note that this analysis was not possible with prior privacy amplification by shuffling results. Recall that our privacy amplification result is an exponential improvement over prior bounds in the high epsilon naught regime, which is the setting we're working in this example. Notice that epsilon naught is order about square root n. Thank you so much for listening.